Hi guys, this is the third video, and in this video we're going to look at transforming an exponential function example. So last video I went through all the different transformations that could occur. Now let's have a look at an example. So this example here is y equals 2 times 5 to the power of x minus 2 plus 1. Now I have seen it drawn like this, y equals 2 and then the time symbol written in. It's okay as well. If you see that, or if you write it like that, that's okay. I tend to sort of use brackets rather than times when I can, though. I feel like it just makes the work neater. It's up to you to decide that or not. So we can get a rough idea about what this is going to do. I mean, we know that this 2 is going to expand the values of y a little bit. It's not negative, so we're not reflecting the graph. It's going to be still in the top two quadrants. The x minus 2 will shift the graph horizontally, vertically. Which one? It's horizontal, isn't it? So horizontally 2 units this way as well. Remember, opposite to the sign, so it goes that way 2 units, and the plus 1 means it goes up 1 unit as well. So what does that mean? Just roughly drawing the graph, you'd think it would be something like this. X, Y. Just change colours for the this plus 1 here means that I'm going to have a vertical asymptote at y equals 1, and it's going to be translated 2 units across. So I think that means that we're going to have, say, 2 units here, and we're going to have a bit of a translation happening up here. Not exactly sure what that translates. I'm not sure when it's going to cut through the y-axis, because this bit here will affect where it cuts through the y-axis, but so does this. So it's not quite immediately obvious. I might do this in green so we can sort of see it. But we know the graph is going to be roughly what, like that kind of thing. So that's roughly what it's going to be like. But we're not too sure exactly what that will be. So we have a y-intercept we don't know. We have an x-intercept. Well, there's no x-intercept in this one. So that makes it a little bit easier for us, I suppose. Okay, so let's have a look at how we would work out what that y-intercept was. So we know the function is y equals 2 times 5 to the power of x minus 2 plus 1. Well, we just need to do our standard thing. Well, what happens when x equals 0? When x equals 0, we work out the y-intercept. So let's look at that. Y is equal to 2 times 5 to the power of 0 minus 2 plus 1, which is y is equal to 2 times 5 to the power of negative 2 plus 1. Now 5 to the power of negative 2 is 1 over 5 squared, so it's going to be 2 over 25. 5 squared is 25, plus 1, so we've got 1 and 2 25ths. So when x is 0, y is equal to 1 and 2 25ths. Okay, that's pretty good. And then we just find out where the x, well, we just confirm the x-intercept actually. I want to make sure it's right. So when y equals 0, what do we have? 0 is equal to 2 outside of 5 to the power of x minus 2 plus 1. So negative 1 is equal to 2 outside of 5 to the power of x minus 2. And then divide both sides by 2. I might just flip sides as well. 5 to the power of x minus 2 equals negative a half. Okay, now we can use our logs from this point on to work out exactly what x might be. So that gives us log base 5 of minus a half is equal to x minus 2. So x minus 2 is equal to, now I'm going to use change of base. Log of minus a half over log of 5. Now, have a look at what happens when I go log of minus a half. Log of minus 0.5. Oh, it doesn't want to do anything at all. And that's because logs of negative numbers are not defined. Okay, log of a half is defined, but not log of negative a half. So from that point on, we don't have to go any further. Okay, not defined for log of negative a half. Okay, I probably could have just said it there actually, to be honest. So there is no x-intercept, and therefore we're right to go. And so on our graph, we can simply fill in that point there as being 1 and 2/25. Okay, done. I'll make that a bit bigger. 1 and 2/25. Okay, just to do one more example really quickly. Let's just say we had very similar one. Let's have y equals 2 to the power of 5 to the power of x minus 2. But this time, let's subtract 1 instead of adding 1, so that we know that the graph is going to cut through the x-axis. Again, I roughly know what I'm looking for. Okay, so I want to get my graph looking a little bit more exact than that by putting in some values, but I roughly know what I'm looking for. Okay, same sort of deal. When x equals 0, what do we have? Y is equal to 2 times 5 to the power of 0 minus 2 minus 1, which is 2 over 25 again, if I can just shortcut a bit, minus 1. And so the y-intercept is going to be, what, negative 23 over 25. So when x is 0, y is negative 23 over 25. So nearly 1, negative 1, but not quite. Y-intercept, sorry, x-intercept is when y equals 0. So we have 2 times 5 to the power of x minus 2. Minus 1 is equal to 0. I've just flipped our sides there. That means 2 to the times 5 to the power of x minus 2 is equal to 1. And 5 to the power of x minus 2 is equal to 1/2 by dividing both sides by 2. Okay, using our log laws, I can say that the log of base 5 of a half is equal to x minus 2. Flipping that around, x minus 2 equals, and then change of base, log a half over log of 5. Now that the logs are all positive, we'll be right for an answer now. And then I'm just going to add 2 to both sides to get log of a half over log of 5 plus 2. P.S. That's the exact answer. Okay, everything I do from now on will be approximate. I might just put it over here just to keep it in the same space. So that's going up there. So that means x is equal to, and what I'm going to do is I'm going to grab my calculator up. There's log of a half already. I'm going to divide it by log of 5. P.S. in case you can't remember, that's the reason why we graphed, the reason why we did change of base is because our scientific calculators have log base 10s. They don't have log base 5s. Okay, so I'm getting here log of 0.5 over log of 5 as being negative 0.43. So that's going to be negative 0.43 plus 2. I'm going to add 2 to that now. Notice I added into this calculation, so I don't have any rounding errors. And that gets me 1.57 to 2 decimal places. There we go. So if I'm now I'm going to do a really rough graph here, but if I'm now looking at my graph, like so, I can fill in my y-intercept. I'll just get that out of the way so you can see what I'm doing. I've got my y-intercept of negative 23 over 25. So that's as good as, say that's negative 1 there. Negative 23 over 25. And 1.57. So if that's 1 there, that's what, about 2 there. So 1.57 is about there. And I can draw my line through here with minus 1 being my horizontal asymptote, and my line sort of going like, see how close I can go, like so. Bit squishy there, but you can sort of see where I'm headed there, and that's the graph done. So believe it or not, the techniques are pretty similar to our other function graphing in that ultimately we want to have a shape in mind that we're going for. We want to know roughly what it's going to look like. And then we're using what's happening when x equals 0, what's happening when y equals 0 in order to get the critical points of our graph. And then we're just graphing it. And that's it. Thanks.